Hello there, my name is Roman Sonnleitner, and my focus at voestalpine for nearly 20 years has been on electrical steel. I invite you to come along with me on a short journey into the fascinating world of magnetism. The term magnetism usually makes us think about how magnets attract and repel each other. You can feel the force between magnets. Magnetism is one of the 4 fundamental physical forces that hold the Earth and the entire universe together. The 4 forces are electromagnetism, gravity, and the strong and weak nuclear forces that can only be measured on a microscopic or atomic scale. While we do not perceive the strong and weak forces, we experience gravity and electromagnetism in everyday life. Electromagnetism is the force responsible for visible light, data transmission in our smartphones or on the internet, and for the rotation of electric motors. And this is electromagnetism that we will be talking about today. But let's begin with regular magnetism, because magnetism is a subfield of electromagnetism and describes the force between magnets, magnetizable materials, and moving electric charges. How can I best describe this phenomenon? The first question we can ask ourselves is this: which materials have magnetic properties? This question is easy to answer because every material has magnetic properties. A distinction is made between different materials. Paramagnetic substances are only very weakly attracted to magnets. This includes aluminum, magnesium, and lithium. In contrast, diamagnetic substances such as copper, gold, or sulfur are weakly repelled by magnetic fields. And then we have ferromagnetic substances that are said to be magnetic because they are very strongly attracted to magnets. Only 3 pure elements demonstrate ferromagnetic properties at room temperature, and these are iron, nickel, and cobalt. Let's take a closer look. How can I visualize magnetic forces and the behavior of magnets? Each magnet has a north and a south pole and is surrounded by a magnetic field. This field can be represented by so-called field lines. The direction of magnetic force is indicated by arrows. They always run from the north pole to the south pole and inside the magnet back to the north pole. The density of the field lines indicates the force strength. The more lines, the stronger the magnetic field. What is so special about magnetic fields? The field lines always form closed loops. In other words, magnetic monopoles do not exist. That would mean that magnetic particles would have only one pole, a north or a south pole. The phenomenon was mathematically explained by James Clerk Maxwell in his famous second Maxwell law. What does it mean? When a magnet is split, it does not create a new isolated north or south pole. Instead, each piece becomes a new, smaller magnet with its own north and south poles, 2 so-called dipoles. So we may ask, how do these magnetic fields interact? When a second magnet enters the system, both magnets exert forces on each other. If you bring 2 poles of the same kind together, they repel each other. If you bring a north and south pole together, they attract each other. This turns 2 magnets into one, and the field lines and forces are added together. The crucial questions remain. What causes magnetism? And how is it created? What types of magnets are there? Let's talk about how they are created first. Magnetic fields are created by the movement of electrical charges. For example, when an electric current moves through a conductor, or by the alignment of magnetic dipole moments in atoms. What are the different kinds of magnets? We will talk about permanent magnets first. These can be magnets in many different forms. Their magnetic field never goes away, and their direction and strength properties never change. The magnetic forces in permanent magnets are secured by the alignment of the magnetic dipole moments in the atoms. Electromagnets are included in the second large group. The magnetic field is formed by the flow of an electric current in the conductor. How do electromagnets differ from permanent magnets? The magnetic field of an electromagnet can be switched on and off, and the direction of the field can be changed depending on the direction of the current. When a current flows through a a weak magnetic field is created that can be represented as circles around the conductor. If the current carrying wire is now wound into a coil, these circular field lines are added together, and a magnetic field is created that corresponds to that of a permanent magnet. The magnetic field strength H in the coil depends on the following factors: the current flowing through the coil, the number of windings and coil size. H can be calculated by multiplying I with N and dividing by L. The achievable field strength is limited because the current and the number of windings are finite. Now we can talk about ferromagnetic material. When we introduce the ferromagnetic material, for example an iron core, into this current-carrying coil, the number of field lines in the coil is increased substantially. Their strength is described by flux density, B. You can imagine this amplification of flux density like this. There are many small magnetic dipoles in ferromagnetic material. As long as no current is flowing through the coil, the dipoles are distributed in every direction, and there is no magnetic effect toward the outside, because the individual dipoles cancel each other out. But as soon as current flows through the coil, these dipoles are aligned along the field lines, increase the flux density, as well as the number of field lines many times over. The field can be reversed at any time, simply by changing the direction of the electric current. This is how an electromagnet is created. And the strength of the magnetic field depends, of course, on the material of the iron core. Our tutorial about electrical steel will teach you more about the important role that isovac plays in this respect. Goodbye until the next steel tutorial.
Voestalpine, one step ahead.